So the new topic that I'm gonna discuss is about the definite integral and the fundamental theorem of calculus. We learned before about the area problem, okay? And the area problem will be solved by using the thing that called definite integral. And in order to compute the definite integral, sometimes it's very complicated. In order to do the Riemann sum, we're gonna study about the fundamental theorem of calculus in order to allow us to compute the definite integral easier. So the area problem that I used to introduce to you before is going to be about we have the curve y equal to fx above the x-axis over the interval ab. I introduced this one to you when we begin studying this subject. And we like the area problem asks you to find the area under this curve over the interval AB. And we not be able to find this area directly by geometry because the side of the picture or the side of the picture that you have here turned out to be curved, not a straight line. So we not be able to just find the area of triangle or rectangle. However, the idea is going to be just we try to compute the area of the rectangle, that we adjust this guy a little bit. So you see that you're going to get some error here and you're going to just have this rectangle and you compute the area of this rectangle. Similarly, you have this rectangle here and you compute the area of this rectangle and so on. So you see that you're gonna get some error and you're gonna get some extra, okay? And sometimes it's gonna like you're gonna have this guy and this guy that will cancel each other. However, it's not gonna be the exact area. So you see that if you divide the interval AB into four pieces, so you have 1, 2, 3, 4. So if you divide this guy into four pieces, you'll be able to get like some error here, some error here, and you're gonna get some extra here and some extra here that seem like not close to the exact one. However, if you divide the interval AB finer, so you see that this one turned out to be 8 pieces, you're gonna get small error. So the error will be smaller in this case, okay? And if you divide this thing into like 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 pieces, like in this picture, you see that you're gonna get the error become smaller. So the idea turned out to be that you're gonna divide the interval AB into many pieces that you have. So you're gonna like divide this guy into 60 pieces, 6,000 pieces or something, that you just compute the area of the rectangle that you have, and then you're gonna sum it up. So you're gonna see that if we fix a positive integer n and you divide the interval AB like it's gonna be x0, x1, x1, x2, xn minus 1, xn, and you just subdivide this one into small subinterval, and like in this picture, and you're gonna pick a height. So you just pick x1 star, pick x2 star, pick x3 star until xn star. So you just pick a height here, and you're gonna be able to compute the area of the rectangle like this. Okay, and you be able to sum the area. So you have the first piece, the second piece, the third piece like this, and you just sum the area up. This sum in math is called the Riemann sum. Okay, so this sum in math is called the Riemann sum. So this thing is called the Riemann sum. And you see that it's going to be the sum that involving the variable n. Okay, so this sum depend on the variable n, because if you change your n or you make your n larger, you're gonna get like the sum that will give you to get to the actual value of the area that you're looking for. So in this case, if we like to increase n, so we're gonna increase n without an upper bound, and you're gonna just use the concept of the limit. So if you use the concept of the limit, you're gonna have limit x go, not limit x go, limit n go to infinity of fn star. So let me conclude this guy a little bit. So you have n, which is the variable in this case, and you're gonna take limit n go to infinity of Sn star, and you're gonna get the limit n go to infinity of Sn star, which is the Riemann sum, turn out to be the area that you're looking for. Okay, so this is how we gonna find the area under the curve y equal to fx. Okay. So in practice, okay, so I say here that in practice, we usually divide the interval AB into n equals subinterval, and you're gonna just choose xi star to be just the xi. So you just choose xi star to be just the rightmost. Okay, so this one is gonna be your xi star. So that will be the thing. You're gonna see this one in the example. I'm gonna do one example for you. So don't worry about that. However, in order to compute Sn star, okay, so you see that we need to compute Sn star before we taking the limit. Okay, so we need to compute Sn star before we taking the limit. You gonna involve the thing that use the formula sum I equal to 1 to n equal to 1 plus 2 plus until n. This guy turned out to be n times n plus 1 over 2. And sum I equal to 1 to n of I square. It turned out to be 1 square plus 2 square plus until n square. So you get n plus 1 to n plus 1 over 6. Okay. And we call Sn star the definite integral of f from a to b, and we will denote by integral from a to b of fx dx. Okay, so this limit of Sn star, okay, is called the definite integral. And you see that, hey, when we like to find the definite integral, do we need to integrate something like this? Yes, actually. So do we need to find this limit? Do we need to find this sum, something like this? Actually, in practice, it's not, but we gonna just do one example that asks you to use the Riemann sum technique here that used to compute integral from a to b. Okay, so it's gonna be limit n go to infinity of your Riemann sum. Okay, so the pink guy is the Riemann sum. Okay, so this one will be the thing that I will teach you first, and then we're gonna compute this one easier by just using the fundamental theorem of calculus. Okay, so let's do this example. We're gonna compute the area. Okay, so we're gonna compute the area under the curve y equal to x squared over the interval 1, 3. Okay, here I'm gonna use the Riemann sum. Okay, so by using the Riemann sum, okay, so in this case, let me draw this picture. So it's gonna be like this, it's gonna be like this, and you have y equal to x squared. Okay, y equal to x squared. So it's gonna give you a parabola. Okay, so this one is y equal to x squared, and it's gonna be over the interval 1 to 3. Okay, so it's gonna be 1, 2, 3. So you would get this one, and you get this one. Okay, so you get this one, and you're gonna subdivide this interval into small pieces. Okay, so this one you're gonna subdivide. Let me just make this one larger and you can see clearer. So you see that you're gonna get something like this. Okay, so it's gonna be small pieces of rectangle. So you have this rectangle, this rectangle, this rectangle, and so on. Okay, so in this case, you're gonna just find the sum of each rectangle. So you see that I'm gonna use alternate color to see, to make you to see clearer. So we're gonna sum this rectangle up. Okay, and in this case, our A will be 1 and our B will be 3. Okay, and this guy is y equal to x squared. Okay, and this one we're gonna partition the interval 1 3 into n equal subinterval. Okay, so we're gonna partition the interval 1 3 into n equal subinterval. How would we do that? We're gonna just draw a straight line like this, and you're gonna have the interval 1 3 1. So that my 1 and 3 like this. Okay, and you're gonna subdivide this thing, so you have 1 2 3 4 5. So you divide this one into smaller pieces like this, and this one will be your x0, this guy will be your x1, x2, and so on. Okay, so you have x1, x2, and you're gonna have this guy which is your xi. Okay, and this one you have the interval from 1 to 3. So let me write number 1 to number 3. So this guy will be your xn. Okay, so that will n. So you divide this guy into n equal pieces. You divide this guy into n equal pieces, and you're gonna see that you like to know the length of this piece. Okay, so you like to know the length. What will be the length of this piece? The length of this piece turned out to be the total length divided by the number of pieces. And the number of pieces in this case is equal to n pieces. Okay, so the number of pieces in this case is turned out to be n pieces, and the total length will turn out to be just 3 minus 1. So you have 3 minus 1. Okay, how would I know that it's going to be 3 minus 1? It is because you have number 3 and number 1 here. Okay, so this guy will be 3 minus 1. Okay, and so you would get 2 over n. Okay, so you get 2 over n, and then what? And then you're gonna be able to determine x1, x2, and so on. So you have the length here is equal to 2 over n. So x1 will be what? In this case, x1 in is so you have, let me write here. So you have x1 will be just 1, which is this number. So it's going to be 1. plus the length, right? So it's going to be 1 plus the length that you have. So it's going to be 1 plus 1, not 1, 2 over n. Okay, that my x1. How about my x2? So if I'm working on my x2, let me making x2 somewhere here. So for my x2, you see that it's gonna be 1. Okay, so x2 is turned out to be again 1 plus you're gonna see that this guy is gonna be the length. However, it's gonna be you're gonna go from 1 twice, 2 times like this. So it's gonna be 1, 2 times the length. So it's gonna be 1 plus 2 times 2 over n. Okay, so that is my x2. How about xi? If you like to have xi, so xi will be here. What does it mean to be xi? Xi means you're gonna have I step. So you're gonna go 1, 2, 3, 4, 5, something like this until this step. So this one is I step. Okay, so this guy is I step. I step turned out to be just 1. Okay, so you begin at the same place plus I times the length. And in this case, you get 1 plus I times 2 over n. Okay, so that's my xi. Okay, so you see that we have x1, x2 until xn, and you have the length. Okay, so the length that I used here is gonna use the notation h. Okay, so my h is the length. So that is my h. So I'm gonna fill 2 over n here. Okay, I have x0 equal to 1, x1 equal to 1 plus 2 over n, x2 turned out to be 1 plus 4 over n, and xi is 1 plus 2i over n. Okay, and you just choose xi star to be just your xi, so it's going to be 1 plus 2i over n. Okay, so this is how we feel. So you see that the thing that we have is gonna be you need to compute h, and my h turned out to be just the total length. My h turned out to be just the total length divided by the number of pieces that you have here. So it's gonna turn out to be just what? Just 2 over n. Now you're gonna compute the Riemann sum. So you have Sn star equal to h. Okay, my h is 2 over n. So it's gonna be 2 over n, and it's gonna be sum I equal to 1 to n of fxi star. So you have fx equal to x squared xi star equal to xi equal to 1 plus 2i over n. Okay, so you're gonna have fxi star equal to 1 plus 2i over n square. Okay, so that my fxi star that I will put here. Okay, so I'm gonna put into this term. So it's gonna be 1 plus 2i over n square. So this is what you have. And then what? And then you have 2 over n sum I equal to 1 to n. And you're going to expand this guy. So it's going to be 1 4i over n plus 4i square over n square. Okay. And so you're gonna sum this one by simplifying. So it's gonna be sum I equal to 1 to n of 1 plus, and you see that it's gonna be 4 over n sum I equal to 1 to n of I. Okay. So, and the next one will be 4 over n square. Let me explain you in this way, it would be better. So this one you be able to expand my sum out. So it's going to be 4i over n and sum I equal to 1 to n of 4i squared over n. And this guy will be 2 over n. Sum I equal to 1 to n. Sum I equal to 1 to n of 1. Okay. And you have 4 over n, which is the constant. 4 over n square with also constant. So it's going to be 4 over n, and you have sum I equal to 1 to n of I, and 4 over n square, sum I equal to 1 to n of I square. Okay, so this one will be this term, okay, respectively. And we know that this one sum I equal to 1 to n of 1 is going to be 1 plus 1 plus 1 n copies. Okay, and for this guy, it's going to be n over 2 n plus 1. Okay, and for this guy, it's going to be n over 6 n plus 1 to n plus 1. So you get 2 over n, and it's going to be sum I equal to 1 to n. So this guy, so you get n plus this guy n equal to n plus 1. The last guy, okay, I forgot 4 over n. So I forgot 4 over n, okay? And the final one will be you add by 4 over n square, okay? And you have n over 6, n plus 1 to n plus 1, okay? So this one will be just this term. And so you're gonna have n and n cancel, okay, and you have 4 and 2 cancel to get 2 and 4, so it's going to be 2 third and n square and n, so you're gonna have 1 n, okay, so this one is gonna be n over 6 n plus 1 to n plus 1, okay, so you're gonna have n. And don't forget the thing that sit outside waiting. So this guy will be, cannot read it. This guy will be this term, and this term. So you multiply this one into the parentheses. So you get 2 over n times n, okay? And you get the second term is 2 n plus 1 over n. The last term you get 2 third, okay, n plus 1 over n. 2n plus 1 also over n. Okay, so this is how we obtain this calculation. And this is the thing that we're gonna simplify to. So it's gonna be 2, and you're gonna plus by 2, 1 plus 1 over n, and you have 2 thirds. Okay, 1 plus 1 over n, 2 plus 1 over n. Okay, so this is my Sn star. Okay, so this is my Sn star ready. Okay, so this one is my Sn star. So if you not have enough space, you may use this above space here, but I already have my Sn star nicely. Okay, so it's gonna be 2. Okay, so this one, I forgot something, right? So I forgot this one must be 4, and this guy must be 4. This guy must be 4, and this guy must be 4. Okay, sorry. Okay, so I multiply by 2. Okay, I multiply by 2 for each term. Okay, so I get my 2 fours here. So the area that we have, okay, so this is the thing that called the Riemann sum. You see, it's kind of huge calculation. Okay. The next one will be we're gonna find the area. The area turned out to be the limit of this Riemann sum. So it's gonna turn out to be limit and go to infinity of, you're gonna copy this whole term down. Okay, so I'm gonna copy this guy down. So I would get limit n go to infinity of 2 plus 4 over 1 over n. Okay, and 4 third 1 plus 1 over n, 2 plus 1 over n, and you have n go to infinity. So you would get 0 for this guy, 0 for this guy, and 0 for this guy. So this one will be 2 plus 4 plus 4 third, okay, times 2. So you get 6 plus 8 over 3, okay, equal to 26 over 3. So this is the area that you have, okay. So this one will be the area of the parabola over the interval 1, 3. Okay, so this will be the area that you have here. Okay, I let you copy this thing down a little bit. Okay, so you see that it's kind of difficult to compute the area by using the Riemann sum. Okay, I will give you one homework on this one. However, in practice, we're not going to use this method in order to compute the area under our curve or under the curve that we are looking for. We're going to use the thing that called the fundamental theorem of calculus instead. But before we go to that, let's go back to this example. So this one will be the notation for the area. The notation for the area is called definite integral. It's definite integral, so we're going to read this one. It's going to be integral. We're going to say that it's integral of fx dx. Okay, this is, we know how to read before. And we're going to add the boundary of integration. So it's going to be from a to b. Okay, so we're going to say integral of fx dx from a to b. The top guy is called upper limit. Okay, and the bottom guy is called lower limit. Okay, so this guy is upper and lower limit respectively. Okay, so we have upper limit and the lower limit. And when we read this one, we're going to read it uh, from A to B. Okay, so we're going to read it from A to B. And this one will be the area. Okay, so in this case, you're going to have the area equal to 26, and this guy is equal to integral from 0, not 0, from 1 to 3 of x squared dx. Okay, so that will be the notation in terms of definite integral. Okay, so this guy is called definite integral. Okay, so if the question asks you to compute definite integral, we're gonna have the following rule. So when you integrate from a to a, so when you integrate from a to a, in this case, the width of the area turn out to be equal to 0. When the width of the area is equal to 0, so you have 0 area. So that number one, okay, integrate from a to a of fx dx equal to 0 due to the width is equal to 0. And when you integrate from a to b of fx dx, it's going to be equal to minus of integrate from b to a. So if you switch between upper and the lower limit, the sign will be changed. Okay, so you have the sign change. And for the last one, when you like to integrate from a to b, okay, so when you like to compute the area from a to b, let me draw one picture for you. So if you have from a to b and you have your curve like this, okay, from a to b, so the area that you're looking for turned out to be this area. Okay, and you see that this one will be here. Okay, and if you have C somewhere, I'm not gonna say that C in the middle. Let's see, that makes C not in the middle. So you have C somewhere between A and B, not necessarily to be the middle. So you have C between A and B. So you see that you're gonna get two pieces. So you get the first piece and the second piece. Okay, so you have two pieces. And the first piece turned out to be integral from A to C. Okay, so that's my first piece. And the second piece turned out to be integral from C to B. Okay, so it's going to be integral from C to B for the second piece. And this one will be just your total integral from A to B. Okay, so this one is integral from a to b of fx dx equal to integral from a to c of fx dx plus integral from c to b of fx dx, where c is lying between a and b. Okay, so you have the first piece and the second piece. Okay. Let's do one example on this idea. So you have integral from 1 to 4 of fx dx equal to 5, and you have integral from 3 to 4 of fx dx equal to 2, and you have integral from 1 to 8 of fx dx equal to 11. So let me use this space to draw the picture. So in this, you get 1 to 8. Let me put my 1 here. Let me put my 8 here. And you have 1 to 4 equal to 5. 4 lies somewhere here. 4 is not in the middle. Sorry. 4 is somewhere here. And 3 to 4. 1, 2, 3. Okay, so you have 3 to 4. The area is equal to 2. Okay, so area equal to 2. Okay, and you have 1 to 8. Area equal to 11. Okay, so that's gonna be the whole picture. So it's gonna be area equal to 8, and you have this one is area equal to 2. Let me write it this way, it would be better. It's gonna be integral from 3 to 4 of fx dx equal to 2, and this guy is your y equal to fx. Okay, so you have the first piece and the second piece. So this one is your first piece. This one is your second piece. Okay, so let me think about that way. So you want to know 4 to 8, which is your second piece. Okay, so, and this is my first. Okay, so in this case, let you have 4 equal to 2. Okay, so that's my part. And you need the second piece like this. So you see that the second piece turned out to be the area uh, so we need number 2, right? So we need number 2. So the way to get the area number 2 will be, it's going to be the whole thing. Yeah, let me, whole area. Subtract by the area from 1 to 4. Okay, so you see that you're gonna subtract by this part. Okay, so you're gonna subtract from the area from 1 to 4. So you have the whole area subtract by the area that I just shaded. So in this case, it's gonna be integral from 1 to 8 of fx dx, subtract by integrate from 1 to 4 of fx dx. So this guy turned out to be 11, subtract by the area from 1 to 4 is going to be 5. Okay, so it's gonna turn out to be equal to 6. Okay, so the total area turned out to be equal to 6. Similarly, for integral from 1 to 3, if you want this area, okay, so if you want this area, it's gonna turn out to be integral from 1 to 4, subtract by the area number 1, right? So it's gonna be the whole thing. Okay, so it's gonna be the whole thing, subtract by the green one. So you're gonna just have the whole thing, which is integral from 1 to 4, subtract by the green one, which is integral from 3 to 4. Okay, so this guy is the green one. And you're gonna get what? I need some space. Let me erase this one. I don't need this one. So I'm gonna get 1 to 4. 1 to 4 is my 5. And 3 to 4 is gonna be 2. So it's gonna be 3. And that's it. Okay. So that one will be 5 minus 2. Or if you want, you may highlight this one with the pink guy. So you have the pink guy subtract by the green one. Okay, so this is how we obtain the area from 1 to 8. The next one will be integral from 3 to 8 of fx dx. So in order to get 3 to 8, you see that it's just going to be number 1 plus number 2. Okay, so this one quite simple. So it's going to be number 1 plus number 2. Okay, and my number 1 will be 3 to 4. 3 to 4, we have number 1. 3 to 4 is going to be 2. You're going to have number 2, which is 4 to 8, is going to be 6. Okay, so it's going to be 6. So this will be your total answer equal to 8. Let me highlight some color for you. So number 2 will be 6. Okay, so number 2 will be 6. So this is my number 2. And number 1 is my green color before. Okay, so that will be your final solution. Okay, so it's going to be 2 plus 6 equal to 8. Okay, so 2 plus 6 is equal to 8. Not quite good. So it's going to be equal to 8. Finally, let's evaluate the following definite integral as geometric area. So you're gonna have integral from -2 to 2 of x plus 1 dx. Okay, so you would like to find the integral from -2 to 2 of absolute x plus 1 dx. So in this case, you're gonna do what? You're gonna draw the picture to see where you have your graph. So this one, if you recall, it's gonna be the absolute value. So it's gonna be a V-shaped graph, and the vertex in this case turned out to be at -1. So you get -1, -2, -1, -2, and 0. Okay, so the graph turned out to be V-shaped like this. And you see that this one gives you y equal to absolute x plus 1. And it turned out to be triangle, the smaller one and the bigger one. Okay, so this one is y equal to absolute x plus 1. Okay, so you may ask me, hey, how would you know this one? You know this guy from, you have y equal to absolute x, right? Y equal to absolute x is this graph. And you have vertical translation. Okay, sorry, horizontal translation to this -1. Okay, so that the way to obtain the graph. And you see that we're gonna get this green area. Okay, and we're gonna get the pink area. Okay, so we're gonna get the green area and the pink area. So integral from -2 to 2 of absolute x plus 1, and go from -2 to 2 of absolute x plus 1 dx turn out to be the green plus the pink. So the pink one, the green one. Okay, so the green one will be 1 and 1. The pink one will be 3 and 3. Okay, so in this case, you would get 1/2 times 1 times 1. And in the pink case, you're going to have 1/2 times 3 times 3. And so you get 1/2 plus 9/2 equal to 5. Okay, so that will be the area. Okay, so that will be uh, your design area. Okay, so it's gonna be come from the area of the pink triangle and the area of the green triangle. For the second one, you like to find integral from 0 to 1, okay, of square root 2x minus x squared. So this will be your function fx. So you have y equal to square root 2x minus x squared. So you get y squared equal to 2x minus x squared. So you get x squared plus y squared minus 2x equal to 0. And this guy will be x squared minus 2x plus 1 plus y squared equal to 1. So you have x minus 1 square, y square equal to 1. Okay, so this gives you circle, center at 1, 0, radius 1. Okay, and it's gonna be only the square root here is positive square root. Okay, so the square root here is positive square root. So it's gonna be just the upper semicircle. Okay, so it's gonna be upper part. So the picture would be what? The picture would be, I'm gonna have to draw the picture somewhere. Let me draw the picture here. So it's gonna be this guy. You have x, you have y, and it's gonna be set center at 1, 0, radius equal to 1. So my circle will be like this. Okay, so it's gonna be just upper semicircle. It's gonna be 0, 1, 2. Okay, so that will be 0, 1, 2. However, you see that the question asks you to integrate from 0 to 1. So you integrate from 0 to 1. It means that it's gonna cover not the whole semicircle. It's gonna be just 1/4 of a circle. So it's gonna be just this part. Okay, so it's gonna be just this part. And so we gonna say that the area that you're looking for turned out to be only a quarter from 0 to 1 of the whole circle. Okay, so it's going to be just this part. And the radius that you have is equal to 1. The radius that you have is equal to 1. So in this case, it's going to be 1/4. Okay, and it's going to be pi 1 square. So it's going to be pi over 4. Okay, so this one will be just the integral from 0 to 1 of square root 2x minus x squared in terms of geometric area. So it's going to turn out to be like a semicircle, and this is how we have this picture. Okay, so I think I'm gonna stop here. Okay, please do exercise 5.2. So we're done with 5.2 now. The next topic that I'm going to teach you is about how to do the fundamental theorem of calculus, and we'll be able to compute the area by just integrating the function and plug in the value, and it's going to be easier than the computing the Riemann sum. Okay, so that will be next topics.